Bufocanoris, the Yosemite toad, this is the animal that I particularly study. You'll notice that its range is very limited. Basically, it's from Ebbets Pass all the way down to the Kaiser Pass and the Immigrant Basin area. It's high elevation. Historically, it occurred as low as 6,000 feet, but at the present time, really, it's 8,000 feet and above. And it goes all the way up 12,000 feet. As some of these individuals can be found. In fact, sometimes even higher than that. This is an animal that is endemic only to California. It shows the highest degree of sexual dimorphism, in particular sexual dichromatism, of any North American anuran. In fact, with the exception of the golden toad, probably anything in the New World. But of course now the golden toad is extinct. The females are this mottled appearing type of an individual with the black irradiation, whereas the male kind of a drab brown color. And it turns out that the males are actually calling, which is unusual for a toad in the western United States, but they do in fact call, and it would appear as though the brown coloration has actually helped disguise them from any predators, because this calling is sort of like, here I am, come eat me, and the brown coloration helps offset that. At least that's the going philosophy at the time. Okay, why are amphibians such important components to the ecosystem? In other words, why are they good bioindicators of environmental health? We've got several reasons. In terms of physiology, if you just look at them straight up, you've got egg masses. Eggs are laid in water. They've got a soft, thin, gelatinous coating, which means that all sorts of things that are in the aquatic environment can permeate right through that egg and affect that egg. You then got aquatic tadpoles that are feeding on the vegetation, the detritus, and other products that are in the water. They once again have gills, so they can pick up any sort of toxins, whatever, in the environment. They can pick up on poor water quality, poor feed conditions, or lack of food. And then you've got terrestrial adults that are hopping around out on dry land, depending on the species, but nonetheless, they're getting out of the water, they're getting out on dry land, they're picking up the conditions of other areas, not just the aquatic habitat, but the surrounding riparian areas as well. And in some cases, like the toads, even into upland and forest areas as well. They've got a complex or biphasic life history, which we kind of already touched on. Once again, we've got eggs and tadpoles, which are aquatic. They go through a process of metamorphosis, whereby they're then a terrestrial adult individual, and thereby we pick up several different habitat types. And within each of these different species, each one has a slightly different set of habitats that that particular species likes. So by looking at a series of amphibians, a series of amphibian species, you're really looking at a wide array of different habitats. And if a particular species of amphibian is declining, it says that there may be something wrong with one of those habitats out there. Okay, another good reason are the ecosystem interactions. We've got tadpoles, which of course are predators on vegetation or herbivores. But in addition to that, they're eating detritus on the bottom of the ponds. And sometimes you'll see little congregations like this of Yosemite toad tadpoles. You'll also see this in spadefoot tadpoles. And indeed, what's at the middle of this little huddle, if you will, is one of their brethren being consumed. They are, in fact, to some degree cannibalistic, particularly in times when times are bad, i.e. there's not a lot of vegetative material for them to eat. They will, in fact, move on to eating other meat sources. Tadpoles aren't just predators, they're also prey. They're food items to various things like this diticid beetle larvae, or predaceous diving beetle larvae, garter snakes. Even other frog species have been recorded to eat tadpoles, particularly bullfrogs. But anyway, they are, in fact, consumed by higher trophic levels. Coyotes have been documented in sifting out Ranomuscosa tadpoles. There have been several bird species, including gulls even, that have been picking up tadpoles as food sources. So the point is that tadpoles are not the top, the bottom, they're right smack dab in the middle of the food chain. Indeed, if we continue up, we go through metamorphosis, you can see that little metamorphosed Yosemite toads are quite small. But if you examine their stomach contents, and yes, this is not an easy thing to do, if you examine their stomach contents, you can see the great the great majority of their diet is comprised of spider mites. I'm sure we're all aware of the little red spider mites, which are very, very small. Turns out they're very high in nutrient value. You look at yearling individuals, and what you see is their diets change ever so slightly. They've still got a good chunk of spider mites, but we also pick up chalcid wasps and spiders. In other words, really small insects and arachnids. We jump up to 1-year-old individuals. They pick up a lot of ants in their diet. Once again, a little bit larger food source. And indeed, if you plot the size of the food items, i.e. mites, owl flies, spiders, wasps, ants, in an increasing order of size, with the different year classes, with the toadlets being in green, the yearling individuals being in red, and the year-old individuals being in the kind of purple color. What you see is that they are in fact partitioning the food resources by size according to the size of the individuals. This is very, very important because we're talking about a species which pops out of the snow, normally in May. This year it's going to be June, it looks like. Comes out, it's got 3-4 months of foraging time period during which it's got to grow, reproduce, and then store up enough fat reserves to get through another winter without starving to death. So they've got a very, very narrow window here. So if you partition your food resources according to sizes, that's going to increase your likelihood of actually being able to make this survivorship. This, I would argue, is one of the things that we've got to be looking at when we're looking at some of these meadow systems and their impact by cattle. What are we doing to this insect composition in those meadows? If we're changing the insect composition, we're actually maybe changing the food resources of animals which depend upon that food resource and are very closely tied to it. And that's an impact that a lot of people don't mention when they talk about cattle grazing. If we look at adult individuals, such as this female here, it's a 3-year-old female, we can see that the diet's yet again changed, once again partitioning the resource. She's feeding on a great majority of crane flies. And these are crane flies, or tupulids, mosquito hawks, the other common name for them, which are quite commonly found in meadows in the Sierra Nevada. What if we change the meadows so that the crane flies disappear? What's going to happen to Yosemite toads? Interesting question. If we look at a 4-year-old male Yosemite toad, we can see the males tend to be a little bit more aggressive in their feeding because of their biology. They actually have a shorter foraging period. So they tend to eat a wide variety of items. In fact, I found stones in their stomachs and leaves and all sorts of other things that are taken incidentally because they're such aggressive feeders. But the point is that they're taking a lot of different insects. This is important because if the insects are impacted, that in turn impacts the toads. But once again, the toads are not the top predators. They're in the middle of the food chain. They are in fact eaten by garter snakes. Okay? They're taken out by avian predators. It turns out that ravens have actually figured out that you can eat something even as toxic as a toad. All you got to do is skin it and then eat everything but the ovaries or the testes. Once again, they're the middle of the food chain, not the top, not the bottom. Okay, population biology. First of all, most amphibians are actually fairly long-lived individuals. This female, for example, which you already saw a photograph of her, looking at annuli in her, we've determined that she's somewhere in the neighborhood of between 22 and 25 years old. Okay? These are not 1-2 year kind of things. You know, Pseudacris virgila is a 3-4 year kind of frog. Most of the rest of them are quite long-lived. Particularly the toads are very, very long-lived, which makes sense. They're active for 4, maybe 5 months of the year max, and then the rest of the time they're basically in a deep freeze. Okay? So they can live very, very long. But in order to make their species continue, one of the advantages to being very, very long-lived is to put out a large amount of reproductive effort every time. In other words, high fecundity. So if you look at a single female, this is a female and a male Yosemite toad. By the way, this male right here is 20 plus years old. When they get that lemon yellow color, that's about at 20 years old. A single female can lay up to 16,000 eggs for Yosemite toads, 14,000 for western toads, and several hundred in the case of Rana muscosa per female. But the point is that these animals have a high reproductive output, long-lived, in a very variable environment. The idea is that by being in this variable environment, having a high reproductive output, what this means is that you're hoping for the good years. And in those good years, that's when you're going to have your offspring, that's when you're going to continue the species. So you're going to kind of be able to coast through the bad years. We also have a variable environment, which I've already mentioned. Let me just kind of run through these. You can see obviously in Sierra Nevada it goes from snow-covered, as we all know really well, to kind of a mucky brown gook to nice green meadow. Okay? And that's the typical pattern in the Sierra Nevada. So a very, very highly variable environment. That's the point I was trying to get at. The problem is that there are several other factors that control what goes on in these frogs' lives. One thing is, of course, drought. Drought, as we all know, is a normal occurrence in the Sierra Nevada. But we've got a couple other factors too that have now kind of snuck in their ugly heads. First of all, let's talk about drought. This photograph was taken, and then 24 hours later, this photograph was taken. What the deal was, we had about 2 centimeters of water. The snow disappeared from the bank that was feeding that particular vernal pool, and now what we have is we have muck with tadpoles swimming around in the muck trying to survive. And it turns out that physiologically these things then kick into high gear in terms of metamorphosis, and sometimes they'll actually get through metamorphosis in the muck. And then the problem is they're very, very small when they get through metamorphosis, and they've got to then make up the difference as little metamorphs. But if you follow this along, more often than not, what you end up getting is this kind of black, oozy slick of dried, desiccated, dead tadpoles. And along about 93, I guess it was, there was a very, very big drop-off in the number of ponds that actually survived, and there was just complete areas that there was absolutely no successful reproduction in at all, period, as a result of the drought disease. We've also got this insidious hole in the ozone over the Antarctic. I was down in Australia a couple of years ago at the World Congress of Herpetology, and it was very interesting to me to go down there and watch the television news, because on television news, one of the first things and last things they give you is your sun exposure rating. The ultraviolet light levels down in Australia are so high now that most people cannot be outside more than 10 or 15 minutes without getting severe sunburn. And in fact, they've got all kinds of problems now down in the Andes of South America, for example, with the sheep with the cataracts in the eyes as a result of UV irradiation. And as it turns out, many high elevation forms, such as the frogs that we have here in the Sierra Nevada, actually have melanin coats to their bones to protect the bone marrow from this mutagen effect of ultraviolet light. And in fact, there have been several papers out recently, Andy Blostein up at Oregon State University, talking about the mutagen effects of ultraviolet light. And it appears as though, in fact, UV irradiation is increasing around the world and may be affecting the frogs, and this may be part of the reason for the decline. The important point here is that I'm trying to say that, hey, we've got a worldwide amphibian decline going on here. We've got a couple of, quote, smoking guns as to why this is actually declining, but the argument that I'm building for here is that that may not really be the base problem to the decline of many of the amphibian species. So what are the factors contributing that we know? Okay, we've got all these spooky things. What are the things that we know? Management practices. Now we're getting to the meat and potatoes. Exotic species introductions, multiple use, and then, of course, overharvesting has to be mentioned. Bullfrogs. This is a bullfrog tadpole, very, very carnivorous little guy, loves to eat egg masses of other frogs, particularly red-legged frog egg masses. Adult bullfrogs have also been recorded to eat red-legged frogs, but more importantly what they do is they're competing with the red-legged frog for food resources and may actually be one of the major reasons that those animals are in decline. In fact, my office mate down at UC Santa Barbara is actually working on this very problem, and also she's working on this problem in consort with fish and trying to see, kind of weed the system out and come up with models as to what's going on with the population, trying to figure out control measures. The other exotic introduction in the Sierra Nevada, which has been very insidious, are fish. The Sierra Nevada was in fact glacially formed, as we all know, and as we all know, trout were really not native, particularly to the higher elevations of the Sierra Nevada, anything above, 6,000 feet. But along about 120 years ago now, people have been taking these mule trains in, and there's little cans strapped to the side of these mules that have got fish in them. And of course today we've got these really nice fancy tanker trucks and even airplanes that fly over lakes and wilderness areas and drop fish into the lakes, streams, rivers, whatever. There have been basically 3 different species that have been planted everywhere: rainbows, the browns, and goldens and brookies. Obviously the goldens are native in a lot of areas. Other areas they're not native. We've got Lahontan cutthroat trout that have also been moved around that are native in some areas, not native in others. The point is that these animals do in fact feed on amphibians, and in fact have been, if you look at some of Dr. Bradford's research, you can see that there's distribution of fish and frogs tends to be negatively correlated. And of course, if we talk about other introduced species, I'm talking about cows. Cows are a nice little thing, as we all know. That's why we're here today. You take a beautiful, lovely green meadow, which albeit you can all see already has some impacts, add cows, and what you get is a nice mucky mess. The problem is, what is this doing to the amphibian populations? Well, I didn't know quite what to expect today, so I didn't bring some of the good nitty-gritty dirty stuff, and now I'm kind of sorry I didn't. So let me just talk about what I've been doing the last couple of years. What I am doing is I am trying to establish a population model for the Yosemite toad. In other words, I'm taking life history data, punching it into a computer, coming up with a model as to what happens to the survivorship of all these different life stages of the Yosemite toad throughout its entire life. Trying to set up a normal, whatever that means, population, and then setting up other study areas that have various regimes of cattle grazing going on in them. Full-on grazing, a rest rotation cycle, and also some exclusions going on. And then by examining the life history, the growth, the survivorship of all of these different populations, combining all that into the computer, then using this matrix model, try and actually look at what's going on with these species. What do we really need to be protecting? Because quite frankly, we don't know what we need to protect. There's, a handful of papers on the Yosemite toad. There's a little bit more on some of the other species, but we still really don't have a good grasp as to what really needs to be protected for these animals. It's much like the ecosystems. We were having an argument about this earlier. We really don't know what the long-term effects of many of our management practices and what they are. And so that's what I'm trying to get at. The things that I found out so far. We've talked about these little plug holes in the meadow and along stream courses, vernal pools, that sort of thing. As it turns out, the Yosemite toad tends to breed in water that's approximately 4 centimeters in depth. This has been in literature for years. Well, if you take a cow and they punch a hole down, you can get holes that are 10, 15, even in one case I got a 20 centimeter deep hole right there in the area where the Yosemite toads breed. As it turns out, toads have about 4 neurons. One of them is not designed for detecting water depth when it varies in an area that otherwise would not have varied in water depth. So it turns out that they're laying their eggs near these holes or in these holes, and even when they lay them near them, what happens is the eggs actually move and fall into these holes. It turns out that if you incubate a Yosemite toad egg mass at a water depth greater than 4 centimeters, it dies. This year's studies are going to focus on what's actually causing the death. Is it the anoxic conditions at lower levels, or what I think it actually is it's actually temperature? Because at 4 centimeters in depth seems to be sort of where you get a kind of a thermocline, if you will, in terms of the temperature grading during the day in the water. That's where the warmest water is. The other surprising thing I found out this year is that in the literature it's been talking about for years that Yosemite toads take somewhere in the neighborhood of between 8 and 10 days to go through development, from the time the egg's laid until the time the egg hatches. Turns out that's completely bogus. It's actually 5 days, which means that in that 5-day period, these egg masses are getting extremely warm, and this 4 centimeter threshold is the cutoff point. Below that, you lose them. Above that, you keep them. And by cross-comparing the various sites I've been looking at, it turns out that in ungrazed sites, something like 80% of the egg masses hatch. In the full-on grazed site, something like 10% of the eggs hatch. And we're talking, 14 to 16,000 eggs per egg mass. And in some cases, 200 and 300 egg masses with entirely dead eggs. We could argue all day about what the long-term effects are, but I would argue it's significant. This is a classic set of slides from the Highland Lakes allotment that I've shown time and time again. I see Denise smiling back there. She's seen these before. The permittee is taking his cows and driving them away from a campground through this area. Fortuitously, I had just previously surveyed this area. Forgive me for not giving exact numbers, but it was something in the order of I found like 160 newly metamorphosed Yosemite toads hanging out on the banks of this little creek here. Then, of course, after we drove the cows through, I went through and surveyed again. What I found were a great deal of little hoof prints. And in those hoof prints, you look right here, you can see this little blob. At a closer shot, what that blob is the dead Yosemite toad metamorph. I actually found, I think it was 60 individuals that were actually dead. I found another 20 or so individuals that were actually buried under cow pies, because as we all know, cows, just before they jump over the water, usually let go out the back end. And there was a bunch of these little metamorphs that were underneath these cow pies, which probably would not have made it. But more insidious than that, the hoof prints that are along the banks of these creeks have very smooth mud sides to them. The little metamorphs fall into the little mud hoof prints. And then if the sun angle hits it just right, so they've got sun blazing directly down on them, the metamorphs desiccate and die in those hoof prints. They act like little pitfall traps. We'll come back to a few more of the impacts to cattle, but let me kind of finish off with the slides if I can. The point that I'm getting at from here on out is that cattle grazing can't be treated as a sole entity. There are other damages, multiple use damages that are occurring on forest as well that have to be considered whenever you're talking about any management strategy. Off-highway vehicle use, we know the kind of erosion and damage that can cause to the environment. Harvesting, certainly in the case of the red-legged frog, has been very, very significant. It's caused major declines in those animals for frog's legs in San Francisco back at the turn of the century, but also scientific collecting has also had an impact, certainly in the Midwest and the eastern United States. I'm going to take kind of a stylized, hypothetical system. What we have here is we have a snowmelt pool. We have a couple of springs going into a springhead pool. The channel goes in, you say you've got a nice meadow pool going on, which goes down eventually into a lake-type situation. Historically, what you'd have is you'd have Yosemite toads breeding in basically all of these bodies of water. Okay? So they could use pretty much any of the habitat they wanted, fill it totally up, and everything's just fine. This is an advantage because if you add a drought year, in the drought year, of course, your snowmelt pool is going to dry up. Your meadow pool, in a lot of cases, particularly vernal types, will dry up, and you're going to lose that habitat to breeding. But you're still going to have the spring pool, and you're still going to have the lakes that you can breed in the margins of the lakes. It turns out historically, Yosemite toads did in fact use these lake margins. And the advantage of this is that once the drought was over, the populations that were in the lakes and in these springhead pools would then move into these other areas, recolonize them, enlarge their numbers, and expand out from there. The problem is what we did with trout around 200 years ago. We threw them into the lakes, and as it turns out, Yosemite toads cannot breed in lakes where trout are present. And the trout will be present, of course, in the lake itself. Sometimes they're even present in the meadow pools. Sometimes all they've got to do is get into the meadow pools shortly after breeding season, feeding on the eggs, tadpoles, etc., and wipe that whole area out for any successful breeding. So in essence, they may as well be there the whole time, even though they're not. So that takes them out. But yet we still have Yosemite toads breeding in these other headland areas. We then add cows to our situation, particularly the meadow area. And you can see I've decreased the number of eggs up there. I'm not going to say they're going to totally wipe things out. Let's just say they decrease them for now. Okay? Then, along comes a situation like we had just a few years ago. We've got a drought. What happens? Toads can't breed in the lakes anymore. The fish are there. They can't breed in the snowmelt pool. It's dried up. They can't breed in the meadow pool. It's dried up. And even if it wasn't dried up, there's fish there. They can't do that. So what they've got left is this spring pond up here, which is being severely impacted by cattle. So what we've done is we've taken what used to be a normal population in drought conditions with a couple of sinks whereby individuals from those sinks of reasonable to good habitat could move into the other areas down to what amounts to basically marginal habitat that these animals have to spring back from. This, I would argue, is a recipe for disaster. It doesn't take much of a jump from this point to say you add acid rain, you add UV irradiation, any little thing is going to be the straw that broke the camel's back. So yes, it's true. Cows are not the thing that drove the amphibians to extinction. Cows have been around for 100 years. What they did, along with other management practices in the forest, is they set the stage for the decline. And it turns out, if you start looking in the literature about decline of species around the world, the species that declined were species that have been driven into this kind of a situation around the world. And then this big spooky factor, whatever it is, came in and wiped them out. For those of you that may have seen the most recent issue of Natural History magazine, there's an article in here which I encourage everybody to read about the estrogen attack, the estrogen mimicking chemicals that are in our environment. It may actually be finally the smoking gun. It may not be the UV radiation. But just to share that with you. That's what may have actually occurred. But that could only occur if you've got a limited population. And this problem is even more insidious than that, because if you look at a normal situation, the black dots here are various size micro-populations. The clusters of black dots you see here we'll call macro-populations. And then what we have overall in a naturally occurring system is a meta-population, whereby you've got these different habitats or population groups that are completely full. So since there's a surplus number of individuals, they start moving to between these populations, thereby mixing up the genetic structure of these frog populations. But what then happens once again, if you've got a drought situation, the smaller bodies of water, as we already indicated, drop out. But you've still got these larger sink populations that survive and did just fine. So then once the drought's over, once again, the individuals from the sink populations move out into these other areas. Then once these fill up again, we get back to a situation where you can get genetic mixing between these different populations. The problem is, I've already indicated, what we've got is a situation where we've got fish and cattle present. Okay? And once again, we come along with a drought situation. And the net result of that is we've caused a complete extinction of one population right here. We've got these other three populations that are in very low numbers. And because they cannot expand to large enough numbers to really where they're going to send out scouts to other areas, you've in essence formed brick walls between all these different populations. What that does, that causes genetic stagnation in each of these populations. One of the prime ways you can drive a population to extinction is keep its genetic pool limited. In other words, who's to say that this group of frogs over here, the ones that have got the gene that says they can survive the UV radiation, the estrogen mimics? Who's to say that this population over here doesn't have it? And the problem is that what we're doing is we're in essence playing Russian roulette. By limiting the genetic makeup of the overall population, we're restricting them to a limited number of alleles that possibly could, in fact, protect them for this long-term onslaught. So cattle grazing is very insidious in that regard. It is one of the players that helps set the stage for the decline of the Yosemite toad, the mountain yellow-legged frog, the red-legged frog, and others. But basically that sort of wraps up what I wanted to get across today. And with that, if you've got any other questions, we can talk about that, and we can talk about some of the things that we're continuing to do in terms of research.